operating systems lab also due Wednesday. So I was like, I just want to get that done because, like, I know I can crank out a presentation if I need to, but I can't necessarily crank out code, like, because if I get stuck, I get stuck and can't watch about it. So I got that done this weekend.
So, I hope you had a good weekend. On Friday, we talked about things with analyzing discrete data, comparing two proportions, one proportion or comparing two proportions, and the odds ratio. And one important reason for looking at the odds ratio is there's limitations to what we can estimate with certain types of data, retrospective data. Some things that you might like to know, you have to be careful how you set things up for estimating things, right? So, and so the odds ratios are important in avoiding some problems. And so we're going to look at that kind of design issue and then talk about two-way tables where things are cross-classified by two different categorical variables. And again, under the sampling models, we might have prospective data, retrospective data, randomized data, and other things. But there's a couple principal ways that we end up testing some type of chi-square test or a Fisher's exact test for smaller data sets. Right? So in both cases, how the data comes up and how it's designed is a pretty important consideration in what you report. Right? So homework is due today. The plan will be to have one more homework that covers much of this discrete data. Right? Instead of having one do this Friday, we'll prepare one and then have it due after break. So there's kind of one more. There's also the project. There's 1 week after the Thanksgiving break. Projects, presentations come after that. Well, I'll keep talking, about different things, but there'll be kind of one homework that does something out of this chapters 18 and 19, and then a logistic regression problem, 20. So there'll be something that covers this material, but instead of forcing in two short homework to try to get back up to 11, we're going to have one more, and then focus on the project, because the project's a much bigger, more interesting thing to do. So, okay. So, in the number of examples that are in the book, right? So the first case study in this is about obesity and heart disease. And so, in this study, they have a number of people in 1976 who have a body mass index greater than 30, or not, or body mass index less than or equal to 30. So body mass index is measurement of weight versus height, or height squared. So there's a conversion to the score. Body mass indexes in the lower 20s are 20 to 25. I don't know exactly the scale, but are much thinner, healthier. Over 30 is considered obese. Some people do get up into the 35s, 40s, 50s, and they're called morbidly obese. That it's going to have quicker impacts on there. And so the people are selected this, and then they follow them for many years. 4 or 5 years. And do people die the outcome, the Y variables. Do the people die of cardiovascular disease or CVD? Yes or no? And so the X variable, right, one variable is this, one variable is that, and this study is prospective. You can estimate things like the chance of dying for people who are obese versus not. But if the study had, 100 people who were over this threshold and 100 people over that, in the study, there's 50% that are obese. But you can't use that to estimate obesity rates in the population, of course, because you designed the experiment to be efficient for something else. You designed it to be efficient for estimating this. So in this case, you can use methods for two proportions to compare CVD, existence of cardiovascular disease, in the two BMI groups. But you won't really be able to say, at a population level, what percent of people are obese beyond BMI 30 or not, right? But you could also use an odds ratio to assess that same thing, right? The odds, all right. So anyway, if it's perspective, it's pretty clear that you can do that and answer your main question very directly with two proportions or odds ratios. A second type of case study that is, the second case study is a randomized experiment. And so you have volunteers who get explained what's going to get on with this study. They give consent, are told about the risks, they're screened for things that would make this a dangerous thing for them to do, and they're randomized. Randomized here, and they either get vitamin C or cold medicine. I have cold written down there, but maybe it's vitamin C or not. That's what this means. Sorry, my notes are a little abbreviated. Vitamin C or placebo would be one way to do this. So is taking vitamin C early, right, going to help you during food or cold season? And some of these people get the flu or cold, and some do not get that, and some of these get the flu or cold, right? And then this. So again, this also is prospective, in the sense that you're randomized and you see what's going on. And so you can use comparison of proportions, again, to directly answer the question you want. Does being in one of these two groups give you a lower rate of flu or cold? So you can use two proportions, as you might think, comparing these two groups. Odds ratios also will address that same hypothesis. Are the rates the same going through there? So in the first one, it was not randomized, but the groups were selected and they were followed forward in time. This one is randomized, so it's also prospective, and it's pretty easy to see what the analysis is. Based on the study, you can't say what percent of people are consuming a high degree of vitamin C in the population. It's not a survey that way, and the volunteer certainly it's set up probably to be pretty close to equal numbers. You don't know those rates in any type of population, but that's not your main question. The third type of study that's done here is called case control. And in this study, there were 86 lung cancer individuals with lung cancer, and then there were 86 controls. So these match on various characteristics. And it's not described as a one-to-one match, like you take each case over here, these are called the cases. Right? And these are the controls, and so we see what disease they've had, and then it's going to ask a question about their background. Right? And in this case, it asks, did they smoke? And so the table that gets, this is then retrospective. Right? So it's something in the present condition, you know, what disease they have, and then looking at something in their past to try to look at association. Right? But it's retrospective. We're not following these individuals forward, so these groups are defined by what disease they have, which is seems a little bit different than randomizing them to a treatment, and it is. So if you make the data, we'll write down the data for this. The numbers and so on for the other ones are in the book. Right? And in this one, you know, there's the cases. Right? And then the controls, they do not have cancer. There's 86 of each of these. Right? And of some of them are smokers and some of them are non-smokers. And of the 86 that had lung cancer, 83 were smokers and 3 were not. And of the controls, 72 were smokers and 14 were not. Right? They weren't chosen to be smokers or non-smokers. They were chosen based on that. Right? And so what question do we ultimately want to answer? Right? We want to answer a question, is smoking associated with lung cancer? Right? But the thing that you directly get out of this is, you know, among this group, right, among this cancer group, what proportion are smokers? And among this group, what proportion are smokers? But the probability of being a smoker, you know, right, among those with cancer, and the probability of being a smoker among those that do not have, you know, lung cancer, is not really the primary question we want to answer. Right? We really want to turn it around and look at things the other way. And we want to really look at the chance of cancer among smokers and cancer among non-smokers. Can we estimate that directly here? So cancer among smokers. Well, you know, it'd be 83 over those two. I guess you could estimate that proportion, but there's a problem. Right? Is if we've chosen an equal number of cancer and non-cancer patients. So that's going to affect the rate of cancer among smokers. It's also going to affect the rate of cancer among non-smokers. Right? Among the non-smokers, you know, the rate is 3 out of 17, which is a very high rate of lung cancer for non-smokers. Right? This study's been set up to have a richer mix of people with the disease so that we can estimate associations better. It's very hard to estimate things that affect a rare condition. Right? If there's something that, you know, if you have a haystack with millions of pieces of hay and there's one needle in there and there's a few characteristics of these things, trying to predict that extreme is often very hard to do. But if it's more 50-50, trying to separate some out, it's easier to do. So these things get a more equal mix. There's not 50% cancer in this population. It's chosen that way. So also the estimated percent of cancer among smokers is not really representative either. So we can estimate these. So yes, we can estimate those things. The book has a chart with a little check to say what you can estimate. But this is not the primary question. That we'd like to to see. And so we can look at what would happen, right? Is, let's suppose, if we put the probability, there's something called a relative risk, right? So a relative risk, or relative risk, RR, would be something like the probability of lung cancer among the smokers divided by the probability of lung cancer among the non-smokers. And in this type of retrospective study, we can't actually estimate this because the mix of lung cancer has been distorted by how we've done the sampling. Right? And so we can't really estimate this thing. So let's look at something like that. Suppose, in reality, the relative risk is 4. So that the numerator up there, the probability of lung cancer among the smokers is 40%, but the probability of lung cancer, right, among the non-smokers is 10%. Well, in the general population, that would be very high. But maybe these people have other risk factors that make them they live with other smokers, they do, they are environments where there's smoke, they work in jobs that maybe have some risks. So anyway, it's more. So the ratio of these two things would be a relative risk of 4, right? But now, let's select 50% smokers and 50% non-smokers into our study. And let's put together a table of what we would expect to see and then calculate what the relative risk would be estimated to be. Right? So, we had 86 in each group in the, let's see, if we had 50% smokers and 50% non-smokers into this study, right? No, that's not what I'm going to, not smokers. We picked 50%, I'm sorry, I have one thing written in my table and one thing written in words. But if I fix, so there's individuals who have cancer, and individuals who are out of control. And so if we have 100 here and 100 here, right? What is, maybe I do mean that, okay. So let's say, suppose, let me do a calculation and then we'll come back and clarify these things. So what is the probability of smoking given that somebody has lung cancer? I'm interested in this because I'm going to pick 100 people with lung cancer. I want to know how many I would expect to have been smokers. Right? Well, it's a probability, can be written as a probability of smoking times a probability of cancer given smoking. This is a little application of Bayes' theorem over the probability of cancer. A little calculation from Bayes' theorem, if there's 50% of the population are smokers. So that was what I meant. Right? We're going to select from a population that has 50% smokers. This could be by age group, by other indications, and things like that. And for the 40% chance that they have cancer. Now, cancer overall, there's 50% smokers, and they have a 40% chance. And so there's a 50% of non-smokers and a 10% chance there. And so this thing ends up being 0.8. If you do a similar thing, what's the chance of somebody smoking, given that they have no lung cancer? Well, if 50% are smokers, and to have no lung cancer among smokers, is 0.6, and then this goes down here. Then among the half of the non-smokers, 90% of them do not have cancer. The rate of smoking among those without lung cancer would be 40%. I want those two probabilities because what I'm thinking about on the previous page is I'm going to pick a certain number of smoker with lung cancer in a certain group. So what I mean here, suppose in the population 50% smoke and 50% don't smoke or didn't smoke right in the past, right? Now my case control design, I pick 100 of each. Okay. Now some of these will have been smokers, and some of them would be non-smokers. Okay. So the chance of smoking from the next page, right? Chance of smoking, given that you're cancer, was 80%. Right. So using 0.8 from next page. Among the controls, the chance that they smoked, did not have lung cancer, was 40%. So there's 40 over 60. So this is what data we would expect under this type of sampling design, right? This then adds up to 120, this adds up to 80, and our relative risk estimate, right, estimating the chance of lung cancer among smokers versus lung cancer among non-smokers, well, among smokers, it was 80 over 120. Right? But among non-smokers, it's 20 over 80. And this thing ends up being 6, right, as an estimate. And the model, assuming these relative risks, we should be trying to estimate something that's 4. But because we've done a sampling that fixes this one dimension and is not prospective, but because it's retrospective, it runs into these problems where we can't tell what that odds ratio is. It's kind of confounded with the original sampling that we did. And so relative risks for the question we really would like to know end up being biased with these retrospective ones. Instead, we can estimate the odds ratio, right? And in this case, so there is a 0.4 chance of cancer in one group and 0.6 in the other one, and 0.1 and 0.9 here. So that's like 4 over 6 times 9. So that's like two thirds, right? 2/3 over 9. So that's like 3. That's like 6. The odds ratio is 6. The estimate from our table, right, that we would have, that two-way table, would be 80 over was 80 times 60 over 20 times 40 from those tables, and so there's 4, and well, so that's 6 over 4. There would be 6. So the odds ratio from this retrospective study, right, if we had exactly the expected amount of numbers, would come out to be the right value. So the odds ratios work out, right, for things like that. So in part, that's why the odds ratios are developed and used, is they work whichever way you're looking at things, because the kind of the effect of the which side you sampled on, or if you sampled on one side or the other, gets kind of washed out because of all the ratio over ratios. And so we can still use odd ratios in retrospective studies. So kind of the conclusion and kind of the message of this, right, from chapter 18, right, in retrospective studies, use the odds ratios, right, to test for independence between the variables, to test for the effect of one variable on another. In the perspective of randomized studies, it's fine to estimate the thing we would want by comparing two proportions, but you could also use an odds ratio, and so a lot of medical fields prefer to do that. But any questions? I didn't explain in all that much detail what happened with these examples of Bayes' theorem, right? But the purpose of kind of going through this calculation is, you know, we're going to sample a lung cancer group, and to think about how many smokers we need that probability. So we got to kind of reverse what would be the natural way to state things, and that's what this does. Right? So not so much a technical thing with new formulas, but an important interpretation. Right, and so that's kind of the main thing that's added in chapter 18, right beyond those. Chapter 19 extends this, looking at two-way tables of counts. And so in a two-way table of counts, you have one variable and another variable. They might be predictor outcome, they might be just two different variables that you're looking to associate. And there's a number, and they're categorical, and there's a number of levels of the first variable, and there's a number of levels of the second variable, and these are rows, so there's a certain count of individuals that would be to the X variable would respond and get classified in a certain row. That adds up to our sample size N, and individuals would be classified according to the second variable, C1, C2, to C sub j. And then we also get, because everybody's asked every single question, you know, we get the number that are in each of these different cells. So N sub I j here is the number of individuals cross-classified into X level I and Y level J. Right. Sometimes Nij is called Xij instead of, you know, a count. There's another symbol for a count. It's also the observed number in here. I find across textbooks and illustrations quite a lot of different notation for talking about the counts. Right? Some people would say this is N, so N1 plus, you know, N2 plus, N sub I plus. They would do something to kind of say you're adding over all these subscripts here, and then this one would be N plus 1, N plus 2, N plus capital J, to say you're adding down this. So depending on different textbooks or sources or online things that you might look at, it might have slightly different notation. But it's somehow giving you a depiction of that. Right? And a 2x2 table like this Right? Doesn't seem that complex, but there could be many different ways you could get these counts. And so those are called sampling models. There's a bunch of different sampling models the book talks about. It's not as critical right now that we, examine in great detail what those mean, right? But those different sampling models describe how do we get the n sub ij's. And these are, there's an apostrophe there. And these would be different sampling models that could be used for different things. One possibility is n sub ij is Poisson. And all the cells are independent of one another. There's a certain rate at which things are going to show up with different characteristics, and we keep sampling for a while, and then they keep coming at their different rates, and then we stop sampling, and that's what we have. Right? So they're all independent of one another. Another possibility is that we have a plan. We're going to sample n individuals. So then all of the nij's together, the whole vector or set of them, has a multinomial sampling model where we have n, and n is fixed sample size, fixed or chosen sample size, how we plan the study. And then there's probabilities that go into each cell. So Pij is the probability that a randomly selected person is in cell ij when they're classified. And those probabilities across the entire table add up to 1. Now in probability theory, if you read a book that does more theory with discrete data and things like that, if these are all independent Poissons and you conditional on the fact that you had n, right, then there ends up being a relationship between these rates and these probabilities, right? And they're kind of proportional to one another. So the places that have higher rates and it's accumulating faster get the higher probabilities. And the Pij's are proportional to the rate there, standardized by the kind of the total of all the rates. Right? So we could have that type of sampling. Another way that we could end up with this table is something called product multinomial, right? Or product binomial if it's only 2 by 2. Right? So it's possible, like in a designed experiment, you have a certain number you're choosing for each category. And then you choose 100 of each category, and then your responses are which of the different other levels they come in. Right? And so the product multinomial occurs if we choose sample sizes R1, R2, up to R sub I, if we have I groups, and we add them together, and that's our sample size n. And then within each row, they're classified into columns. So responses in each row are classified into the different columns that are there. Right? So kind of like our retrospective study where you had cases and controls. The sample sizes for in one dimension are fixed, and we see how they fall out in terms of the other responses. Right? In this case, I'll have to write it on the next page to write it to be able to product multinomial. Right? The probability being in a certain cell ij relates to the proportion that are in that, say you fix a row, in row I, so proportion in row I. And then there's a probability of being in column J given that you're in row I. So this is a conditional probability. Of being in row, conditional probability of row of column J, sorry. Of all those individuals that we sampled from row I. So this type of product multinomial can arise prospectively. Right? You can do a population survey and classify some people as, working full-time, part-time, and so on, or having certain education levels at the base year, and then following them for the next 20 years of their lives to see how things turn out. And so you have a certain number that are, less than high school, number that are high school graduates, some college graduates. You could have, many groups and follow them over time. And then, their outcomes could be, are they employed, full-time, part-time, or something like that, or, their financial, kind of social economic status level, 10 years, 20 years out. So it can be prospective. You could do a randomized experiment, right? And have 2 or more groups that get randomized, like it's not unusual. So the biostatistics at George Washington University, when I was leaving, was just starting a study called GRADE, which was going to look for people with type 2 diabetes that were already on medication. What was the impact of adding a new medication on there? They would take metformin, but then there's different aspects, different medicines that get added on to that to help diabetic function, production of insulin or uptake of insulin or other things, right? And so there's going to be 6 groups was the initial plan. So that people will be randomized to one of 6 groups, and then they'd be followed for at least 3 years and see what performance there is. So this could be prospective, right? But there's also retrospective. That's possible to think about with this design. Okay? And so retrospective, you can have people that have different levels of cardiovascular disease. Some people might have had a heart attack or stroke as an extreme. Others might just have hypertension. Others might have milder hypertension or some other complications. So you might have several groups, and then you're looking back over at time into classifying them based on their physical activity and diet and other complex things. Right? The final kind of sampling model in this is called hypergeometric. Right? And in this case, the counts for the rows and columns are fixed. So that things are set up so that you have a certain number of rows, and you have a certain number of counts in all the columns. And those add up to the rows and the columns add up to our sample size n. And the thing that we don't know is how things are cross-classified in there. Right? And there's something called a hypergeometric distribution for that probability model that we could study. Right? And so in all before really kind of this phase, right, if this is really the sampling, we probably would analyze things for this type of model, but the other ones before that, you can analyze in different ways, but the typical way is really to condition on things in the rows and columns, and analyze it as if it was hypergeometric to see if there's an association, to kind of reduce that variability by restricting things. And then there's a couple tests that get done, right? So a first test, right? So hypotheses that we get interested in in this, the simple statement is, are these two variables just simply related? The two variables, x for the rows and y for the columns. The two things that define that are those two variables related. And the null hypothesis becomes that there's no relation. And the alternative becomes that they are related. And exactly what you phrase in terms of no relation or not depends a little bit on that sampling model, right? Because if you sample according to groups, you're really saying, are the proportions the same across those two groups? If you're just sampling and then cross-classifying it in 2 dimensions, they can be thought of as independent. So sometimes they're independent, and sometimes, depending on the sampling model, it's better to think about it as homogeneity or equal proportions in the second variable across levels of the first variable. In the case, but we would calculate, there's kind of a couple ways to test. One is a chi-square test. Which is either an x squared statistic or a likelihood ratio called a g squared, what I call g squared. Right? Or something called Fisher's exact test. That gets probabilities from the hypergeometric. Right? Distribution. And so under in the chi-square, right, test, we're going to calculate how many we expect, what type of expected counts we expect under the null hypothesis. Under a Poisson sampling model, the mean and variance of the number there is that expected number, so we can get a standardized z-score. We can square that and add them up and get a chi-square statistic. And if that's large, we end up rejecting the null hypothesis. So this is our table with rows 1 to I and column 1 to j and sample size n. And this is the number in this row, and this is the number in this column. In this ij cell, right, under the null hypothesis, we think of the proportions being the same by row or column, given the other, within, across the other levels, or independence. So we take the number that of cases, how many we expect to be in there. We are going to put in an estimate of the probability of being in there, but under the null hypothesis, we're going to take the number that are in that row, right, times the proportion that are in that column. The probability of being in that row, probability of being in that column, based on our data, and we get a little cancellation here, so it's often written as Ri times Cj over n. And that's, I'm going to call E sub ij, right, the expected count. That you would see in there. And what we have to compare that to is the observed count. So under a Poisson sampling, right, the expectation of the observed count that we would have there, right, would be this expected value, and also the variance of the observed count. What would be this expected value, because the Poisson has an equal mean and variance. And so we can take this observed count in the cell, and we can subtract that estimate of the expected under the model. Right? But as counts get bigger and bigger in tables, you get more sample sizes, you get more variability. Right? So we're going to divide by the square root of that. The counts in the table are not really independent because you get more in one, it gets less in another place, and so on. There's kind of a trade-off. It all adds up to the sample size. If we just added these all together, there'd be some positive, some negative. So we're going to square all of these, square these deviations, and then add them all up. Right? And so our statistic, what's called Pearson's x squared statistic, is a sum over all the cells, sum over I and j. So this is the sum over all the cells in the table of the observed count ij minus the expected count squared over the expected count. And under the null hypothesis, this statistic in large samples with expected values that are not so small is distributed like a chi-square distribution, and its degrees of freedom are I minus 1 times j minus 1. And so the farther the observed are from the expected, the more the model seems to fail the null hypothesis of independence. And so we'll reject the null hypothesis, H0, if our x squared statistic is greater than our chi squared with its degrees of freedom. If it's greater than the 0.95 cutoff. Chi-square distributions kind of, they can look like this if degrees of freedom are above 1. And this upper tail here, this 0.05 upper tail, if our observed minus expected is big enough relative to these expected, like if these square distances are big, we're going to get a big sum there, and we're going to reject that null hypothesis. And conclude that there's independence or equal proportions across those, equal rates of the other variable. Right? The other statistic that gets used is called a likelihood ratio. Chi-square ratio. Oops. Ratio chi-square. We call this g squared. And in this case, you take 2 times the sum over the cells, right, of the observed count times the log of the observed count over the expected count. It's a slightly different statistic. But again, it's derived more from the sampling models, from the multinomial or Poisson sampling models, and as a likelihood ratio, and still is going to have the same large sample distribution, meaning that the expected counts are not too small, so you're not dividing by a tiny number when you're doing logs or taking a ratio, right? And again, if it's large, you reject. So let's look at one example with this, and then maybe we'll be able to take a, so let's see, where's our, sorry, there it is, right? So in one of the data examples from the book, right, there is this, copies of notes. This was case study, the first one in chapter 19. And so in this case, there there were resumes of individuals who were made to look male, and then resumes that were made to look female based on names or some other aspects of it. So somebody reading it could possibly read in that based on the name and some things that it was male or female, and then they had to choose a certain number of individuals to be promoted. And this is about, is there unconscious bias or more explicit bias for some people maybe in terms of males and females for promoting for them for certain jobs. And the case study does more of a description. So the answers were, yes or no, 24 males, 24 females, resumes. These few commands here set up a matrix and provide convention names, right, like this. And so right, so there's 20, how many there are, right, 48 in all. There are 24 males, 24 females. So if we expect the promotion to be independent of these two groups, or promotion to happen at the same rate in these two groups, in that first cell there, so 35 were promoted, so 35, and there's 24 in that first row divided by 48, we'd expect 17.5 to be there in that cell. Of the 24 men, we'd expect their rate of promotion to be the same as overall, 35 out of 48. We'd expect about 73% of the men to be promoted and 73% of the females to be promoted under this. And since there's 24 of them, we'd expect it there. Same thing for the females. We would expect 17.5 there. There's obviously some discrepancy. For the second column, there's 13 only that were not promoted. Of the males, half of them were males, so we'd expect half of them to go there. So we'd expect 6.5 there, and same 6.5 down below. So there's a chi-square test that does this, that can report these expected values, 17.5 and 16.5, like we would expect. Right. In this case, there's a 2 by 2 table, so there's 1 degree of freedom, 2 minus 1 times 2 minus 1. Right? Once you fix the rows and column totals, once you choose one of the cells, it tells you how many are in that row and then the next row, and so it all has to add up. There's only kind of one free choice. If the proportions add up to, anyway. If you were modeling these data without the independence assumption, you could choose 3 proportions. Right? They have to add up to 1, or the sample size has to add up, so you get 3 choices there. But with independence, you get a row proportion and a column proportion. So there's a difference of 1 parameter between those models, and so the chi-square ends up being that. Just doing our calculation, so if you do promo minus these expected numbers, those are how they're different in there. We would standardize those by, say, the square root of the expected numbers. These are kind of the kind of standard, the relative deviations. No individual one is greater than 1.96 or negative 1.6, like a standard normal scale. But the whole pattern of them needs to be considered. So if we square all of these things, this is how much they're going to add into the statistic, right? Because how they're doing that. If we add all of those things up, maybe what happens? Okay. Add all those up. Oops. See my square. See if this work. Oh, so somewhere in there, I got, let me go back some, I wanted this sum here, right? Anyway, so somewhere, the sum of this chi-square test, right, those things add up to 5.17, and it tells you the p-value is 0.022, So based on that, we would reject the idea that these things are independent. There seems to be a definite difference in proportions. Right? The chi-square, the 95%, the quantile, 95% quantile for a chi-square 1 is 3.84. So we're behind that, we're ahead of that. And the chance that we're above, at 5.196 or above, is the p-value, the probability we're at our observed value or more extreme under the null. So there's 5.1692, just 1 degree of freedom, is our p-value of 0.02299, and so on. So we would reject. There is this continuity correction that can be done. It adds a half to some of the cells and takes away half from some of the cells. So it is done because we are doing something that is discrete with counts, and then using a normal, essentially, or a chi-square smooth distribution to try and evaluate it. Right? And just like with a binomial, you can do the proportion test, you can do a little bit better with a little continuity correction. It doesn't here. Right? The book mentions this. So with the correction, the p-value is actually a little bit larger. So this would suggest where the continuity correction kind of makes this difference. Why is it making such a difference? Right? It's in these expected values that we have. Where were they? Right? Some of these expected values are kind of small, like 6.5. Right? Generally, you want those to be bigger than 10 for a small table. So the normal approximation isn't really so great in there. And so you get this discrepancy. So this is only 48 resumes, and so it's not a big sample. It is kind of suggestive of significance in kind of the extreme differences that are there, but it doesn't quite pass that test. The other thing that can be done with the small sample sizes is this Fisher's test. The promo was just the data set that's there, and you run that, and it gives a p-value for testing that same hypothesis of 0.049, just a little bit below. So if you really want to emphasize that 0.05, you could report to all of these different statistics and come up with a story that it appears that this is significant. In these small sample sizes, the Fisher test, which we haven't really defined yet, is probably the one that is best to use, and would give a p-value that would make kind of be the most defendable. It doesn't have this large sample aspect to it. And so just briefly, on Wednesday we can come back and look at it just a bit more before moving on to the rest of chapter 19. This Fisher test. So we use, in this case, the hypergeometric distribution, right, to give us the probability we see a certain table. And if we have a 2x2 table that has counts A, B, C, C, and D, they all add up to n. Well, there's n ways to choose the rows. N choose A plus B to choose the rows. And then the idea is that we've picked A plus C different values. Wait. I pick A plus C. And then a certain number of them, of this A plus C, end up in the first row. And a certain number of these end up in the second row. So there's C plus D. Right? Choose C. And so under that model of the fixed rows and column numbers, we get a certain probability of that table. If you randomly associate it and filled it in, that's what you would get. There's only so many tables that can happen, particularly with 2x2. Right? You could make A one more, or you could make, and then that would mean this would have to decrease, and this would decrease, and this would go up by 1 to make everything balanced, and all the margins stay the same. Right? So you in the Fisher exact test, right, enumerate all tables with the given margins, the given marginal counts, that are around the side, b plus d for this one, right? Calculate the odds ratio for each table. And so we're going to look in the direction that is away from the null hypothesis from where we are. So the null hypothesis is an odds ratio of 1. And so we're going to calculate, add up all the probabilities of the tables. So our p-value that we calculate ends up being 2 times the sum of probabilities for tables at least as extreme and we'll clarify this on Wednesday, at least as extreme as our observed table. So if our odds ratio is bigger, we're going to look at all the tables that have bigger odds ratios up to the most extreme. Add up all those probabilities of the high-degree geometric, that becomes our p. So we actually enumerate all the tables and get the exact probabilities under that. And in this case, the Fisher exact test gives us a p-value that's. Anyway, so we'll do a little bit more with that on Wednesday, and then talk about stratifying. And I'll take the homework. Thank you.
Thank you.
Thank you. Thank you.
Yeah.
Wednesday? What are your office hours this week?
So certainly between classes,
Okay.
and then a little bit after my afternoon class. The afternoon class is
Okay.
1:30 to 2:35. What is your schedule on Wednesdays?
It's pretty.
Or before this class, do you want to talk about the project?
Yeah, so I've started it.
Okay.
I was gonna do a lesson plan,
Mm-hmm.
but I just don't know like how. Like I have like the basics down, but I'm just not sure where to go from there. So I was wondering if we could talk about it
Sure,
so I can work
sure,
on it
yeah.
over Thanksgiving.
Yep, that'd be great. Do you want to meet before this class?
Yeah, that works.
Okay. That'd be good. I'll be in. So.
Okay.
Yep. So a lesson plan aim for primary grades,
Mhm.
right? And so what the student's going to be expected to do and experience in terms of probability and sampling and is more limited. So you can describe that they might want to relate an outcome to something. They
Okay.
do apply more pressure
Mhm.
to something, and things fly farther, or something
Okay.
that they might manipulate, or they and then how does that connect to something in our class?
Okay.
So if it's two quantitative variables, and then they would do something to make a graph.
Mhm.
That's something that might be kind of fun for them
Okay.
to do. But then you could talk about, take an example, maybe analyze some data that would be kind of outside of that,
Mhm.
or kind of related to concepts that you want to get across
Okay,
to them, so.
thank you.
Yeah,